Hi, everyone. I'm Lei Fu. I was a PhD student in McGill University and Sorbonne University, and I just graduated a few months ago. And today I will present my PhD thesis about exploring the perception of violin qualities, student versus performance level instruments, strings, and soundpost height. Here's the outline. We will begin with background and then explain our research objectives, and then the first study about player evaluation of performance and student violins, and the second study about how different strings affect violin qualities, and third study is about perception of violin samples height differences through a playing test and a listening test. And many researchers tried to correlate the mechanical characteristics with the violin quality. For example, Basinger has found that the good violins, the A0 mode radiated stronger for good violins than bad violins, but they only decided the violin quality based on their own himself and the two violinists' opinion. So they didn't involve a psychoacoustic experiment. So we don't know whether these results, this conclusion is reliable or generalizable. Until recent years, several scholars have conducted the perceptual experiment to evaluate the violin, explore the player's preference about the violin quality. For example, Fritz has conducted two experiments, compared the new violins and old violins by the players, and they found that players could not distinguish new from old violins at better than chance levels. And scientists conducted a series of experiments investigating the players' preference to violins. And they found that players generally are very consistent about their preference to violins. And however, they don't agree each other about which one is better, which one is worse. So based on the previous studies, there's a large amount of disagreement between players. And then we began to wonder whether the violin quality evaluation is just a question of preference. Is there a limit of goodness under which players would agree that the violins are not good? If so, what are the differences between the bad violins and those good ones in terms of perception and vibratory response? And this this idea also comes from the Padler study of Statis' formal study, because he abandoned those bad rated student violins from the selection procedure, because they think they would score the results. So then we began to think, if we use these student violins and very good violins, whether the players can reach a higher agreement about which one is more preferred, which one is less preferred. So then we conducted the first study, player evaluation of performance and student violins. And then we want to explore what factors can affect the violin preference, perception, or quality. Violins can actually differ on a large number of parameters. Are you saying to me? So we are thinking that we can reduce the variability by making a specific modification on a given violin and see how the modification is evaluated. For example, we can think about the bridge, the soundpost, or the tailpiece, or the strings. The bridge and the tailpiece is actually difficult to modify without the presentation of luthiers. And so after the interview with some luthiers, and we decided to start this question from strings and soundpost. So this comes the second study, how different strings affect violin qualities. And the third study, we investigate the perception of soundpost height differences through a playing test and listening test. We will explain this later, why we choose soundpost height differences. So this is the first study to investigate the player evaluation of performance and student violins. We ask violinists to do a playing test. And then we select 3 performance violins and 3 student violins. And 9 violinists participated in this experiment, and they come with their own bow, and they were asked to wear dark sunglasses, and the experiment room, the light was much more reduced, so they cannot see, so they cannot be influenced by the appearance of the violins. And the first phase, we ask violinists to do a preference rating on a continuous scale from 0 to 5. So they rate these 6 violins from least preferred to most preferred, from 0 to 5. And then in phase 2, they do a similar rating process, but we ask them to rate for 5 criteria: responsiveness, resonance, clarity, richness, and balance. For example, we ask them to rate these 6 violins from least responsive to most responsive, from 0 to 5. And after these ratings, we also give them a questionnaire to answer. For example, we ask them, based on which criterion you do your preference rating, and what behavior make you think this violin is most responsive, like this. And here is the results for the first phase. The preference ratings for each violin. So the P1, P2, P3 are the 3 performance violin, and S1, S2, S3 are the 3 student violins. And so the y-axis is their mean rating across 9 subjects. And we can see generally the performance violin were rated higher than the student violins. And then we do the statistical test and found that there is significant differences between the 6 violin preference ratings. However, we don't know which 2 violins rated significantly different. But when we group these 6 violins into 2 groups, performance violin and student violins, we do the statistical test again and found that the performance violin group were rated, on average, were rated significantly higher than student violins. And we also look at the agreement between the participants. here we calculate the inter-individual consistency for each subject. So 0 means that they don't agree with each other, and positive consistency means they have more positive agreements, and the negative means they don't agree with each other. And we can see that these subjects 6, 7, 8 has higher consistency between each other, and these 3 subjects happen to be the 3 professional musicians we invited. And subject 1 has a conservatory degree. Subject 2 to 5 are current undergraduate students, and subject 9 is a current graduate student. This plot is like we investigate the influence of the subject's characteristics on the rating difference between performance students' violins. So this plot, we see the x-axis is the degree. We represent the conservatory degree 0 and current undergraduate student 1. So the current graduate student is 2, and the professional musician is 3. And the y-axis, we can see that is the rating difference between performance violins and student violins. So the mean, for each subject, we calculate the mean performance violins ratings, and then minus the students' violin ratings. We can see that this difference correlates with the degree positively. That is to say, a subject has a higher educational degree, and they will rate the performance violins much higher. And also we can see that the p-value, this relationship is significant. So, okay. And this week, this is criteria ratings, and we in the same way we group these 6 violins into performance violin and student violins, and calculate the mean ratings for each group and for each criterion, and with confidence intervals as well. And we can see that the confidence intervals for clarity, richness, and balance, these 2 groups violins doesn't, the confidence interval lines doesn't coincide. So performance violins was rated significantly higher in clarity, richness, and balance. However, they don't have significant differences in responsiveness and resonance. That is to say, so the performance violins were on average more clear, more richer, and more balanced than student violins, according to the violinist ratings. And the relationship between preference and criteria ratings shows that richness and clarity ratings correlate with the preference ratings significantly. That means that players generally prefer a violin which has a richer sound, and to a lesser extent has a clear sound. And the responsiveness seems correlates with the preference ratings negatively here. And the bridge admittance measurements Okay, so this is not a PowerPoint file, so we can see it all together. So the upper plot is for the 3 performance violins, and the lower plot is for the 3 student violins. Let's see the A0 mode. The magnitude of the performance violins is much higher, we can see that. And also for the B1 minus mode, the magnitude of performance violins is much higher, much more higher than the student violins. However, this is not the case for the B1 plus mode. This seems similar with each other. And then about the, there's another thing need to say is around 1000 kilohertz, we can see there's a peak, there's a hill for the performance violin, but this is not the case for student violins. So this is called transition hill. So performance violins show this transition hill, but student violins does not. So let's conclude for this study. We found the performance violins were on average rated significantly higher than student violins on preference, richness, balance, and clarity. We didn't show these correct ratings here, but just write conclusion here. And the second one, subjects who were professional musicians and or with higher educational degrees, they rated the performance violins much higher than student violins in preference, resonance, clarity, and richness. These 3 professional musicians highly agree with each other in the preference, resonance, and richness ratings. Violinists preferred violins with rich and to a lesser extent clear sound. And the magnitudes of 2 signature modes, A0 and B1 minus, were higher in performance violins than student violins. And the magnitude response of the student violins did not show an apparent transition hill around 1000 hertz. And okay, this is the second study. We studied how different strings affect violin qualities. Also a playing test. In this study, we used 2 similar student violins. They have similar making and similar sound qualities. And we tested 3 types of strings: dominant, Kaplan, and Pro-Arte strings. And this was conducted in 2 places, first in the Oberlin and second in Montreal. In generally, we installed the same types of dominant strings in the 2 violins, and then we change the strings of violin to another strings. In each experiment condition, we ask subjects to compare violin 2 to 1 according to 8 criterion to do a difference rating. And then we compare these difference ratings of different experiment conditions. Then we can see how the strings influence the violin quality. We will explain this in detail. In Oberlin experiments, that is in the Oberlin violin acoustic workshop. So researchers, luthiers, and the players are all gathered together 1 week there for this workshop. So it's easier for to conduct experiments. So we in the beginning, the 2 violins were strung with the same type dominant strings, and the 9 subjects come to play these 2 violins and compare the 2 violins. And so in phase 1,
may I just add something? Yeah, I just want to make clear that we chose this this protocol because you can't really compare the same violin with different set of strings. at the same time, obviously, you know. So you need to have one violin, and then you have to change the strings and compare the violins. And we know that people have a very short echoic memory. So we saw that it would be quite, not necessarily very easy for them to remember exactly how the violin sounded with the other strings. And that's why we decided to have another violin. So here it's violin 1, where, so basically the violin with, for which you will change the strings is always compared to the same violin which doesn't move. So the reference is always there for comparison. We thought it would be easier for people to compare the violin to something which will not change. And then we can see basically the differential between the two tasks. So when it's compared with a certain type of string and when it's compared with another type of string.
Yes, okay. So in the first phase, we tell them that you have 5 minutes to play 2 violins. And at the end, you will be asked to describe the differences between them. And phase 2, please compare violin 2 to violin 1, the reference violin, according to each criterion, and you have 2 minutes for each criterion. So the violin 1, so the name of violin 1 or violin 2 is switched for different subjects. So this is how we do the difference ratings. So for example, for the responsiveness rating, if you feel like violin 2 is as responsive as violin 1, and you give a 0. And if you feel violin 2 is more responsive than violin 1, and it's a bit more, and that's 1. It's moderately more, that's 2. It's a lot more, that's 3. And if you feel that violin 2 is less responsive than violin 1, a bit less, -1, moderately less, -2, a lot less, -3. And so do this difference rating for responsiveness, resonance, power, brightness, clarity, richness, balance, and finally do the overall quality difference rating. And after they do the session 1 difference rating, about 3 days passed, and we ask luthier to help us to change the strings of violin 2 to Kaplan strings. And then we ask the 9 subjects to come back to compare the 2 violins and do the same difference rating as in session 1. And when we come back to Montreal, it's not easy to ask subjects to do a session, and after a few days or a few weeks to come back to do another session. If they were not able to come back, we have to abandon these results. So we just change our procedure. So each subject finish these 3 trials in 1 hour. At the first time they come here in 1 hour to 1.5 hour. And this time we add another type of string, Pro-Arte strings. So in trial 1, it's same, the violin 1 and 2 installed with the same dominant strings as in Oberlin, and the strings were not changed. And then we ask subjects to do the difference rating, and then after the rating, we ask subjects to sit outside to wait. And they don't know what happened to these 2 violins, and the experiment just change the strings of violin 2 to Kaplan or Pro-Arte. And then they come back to do the difference ratings again. So trial 3 is the same thing. And this time 10 subjects participated. Here is our results for Oberlin. we see the y-axis is the mean difference rating. So that is what they did. They compare violin 2 to violin 1. So so the 0 means that violin 2 is as good as violin 1. The positive rating means violin 2 is better, and the negative rating means violin 1 is better. So now we can see that in the responsiveness, so the violin 2 is less responsive than violin 1, and for the resonance and power, violin 2 is more resonant and more powerful than violin 1. But we don't really care this result. What we really need to compare is the blue line and the red line, the difference between these two lines. Because this is how the strings influence the violin quality. And however, the results showed that for any criterion, there's no significant difference between these two experiment conditions. So there's no significant influence because of the change of strings. And for the Montreal results, we can see that the mean ratings has more negative values. This is because the Montreal results, the Montreal experiment were conducted 3 months later, and we think that the violin conditions were changed as a season. So we feel that the violin 2 become worse after we come back to Montreal. So we have more negative values. So almost violin 2 is rated, almost violin 2 is worse than violin 1. But we only need to see how the string changes affect the difference ratings. So the difference between the lines is what we need to analyze, and the statistical analysis shows that only the brightness has showed a significant difference. So when the violin 2 is installed with dominant strings, and it is the difference rating of brightness is significantly higher than violin 2 is strung with Pro-Arte strings. So this is the only significant result. And we also look at the relationship between the difference ratings of overall quality and each criterion, as in study 1. The similar thing is that richness also correlated to overall quality significantly, but this time is resonance correlate to overall quality significantly instead of clarity. Our conclusions for this study, the brightness difference ratings were found to be significantly higher in D1, D2 than in D1, P2 experiment condition for Montreal. And richness difference ratings, and to a lesser extent, resonance difference rating were found to significantly correlate to overall quality difference ratings. As this results has very few significant results, we think there's several reasons. First, this shows that players actually don't agree with each other. They have different opinions. So we lack of significant results. And then the strings we used actually they are widely used among players, so they are of relatively good quality. So maybe this is also a question. And also the age of strings. As in Montreal, we change the strings very frequently. So for each subject, we change 2 times of strings. And then for the last subject in Montreal, the bridge was broken during the changing of string. So then we cannot include more subjects. So the number of subjects also are a factor. Okay, now we explain this.
Lei, maybe before you move to the last study, I'd like to add something because basically with all the comparisons we've done with instruments, until Lei's study was always, with different instruments, and each different instruments will differ by many, many variables. So we thought, okay, let's stick to the strings because then it's the same instrument just with different strings. So to some extent we reduce the variability. But then you realize that, yes, but there are also disadvantages because you can never have the same instrument with different strings at the same time. So that's one problem. The other problem is like by changing the strings so often, as Lei said, we had problems with aging the strings, with the bridge deterioration, which didn't like to be with so much constraint by changing the strings all the time. So that was another problem. And then we realized that we end up with the same disagreement between players. So although players all agree that strings can make quite a big difference on the sound of a violin and can change the sound of a violin quite a lot, because they all have different opinions, in the end, we barely don't see anything. So we were very surprised to see so little significant results, but that's again because of the variability in terms of players' opinion. And so this is just to show you as well that, you can have what you think is quite a clear-cut experiment to conduct, and you feel like you will have some interesting results, and at the end it's just blurred in noise because of this huge disagreement between players, and because of the difficulties of running these experiments with lots of rigorous constraints and a scientific methodology. Yes.
Okay. Okay. So the third study we
can you hear me?
Yeah.
Yeah.
I would just add that these particular strings may not also have been hugely different from one another. So that was another potential problem.
But they were still different in terms of prices and of one.
This is Fan Tao.
Hi, Fan.
They're quite a bit different for synthetic core strings, especially the Kaplan and the other two.
Okay, good to know.
And the amount of damping, which is highly correlated with the brightness, is quite different for the Pro-Artes and the dominants and the Kaplans. So there are differences.
So you would have expected more differences as well, because I remember.
I don't know. I'm just saying that, yeah, I mean, these strings are probably more similar than, let's say, steel core strings, but for synthetic core strings, they are quite a bit different.
Yeah. And you see the Kaplan is right in the middle. It's not even the one which is extreme, so it was quite surprising. We would have expected more differences. But thanks for jumping in, Fan.
Okay, so the string prices like Pro-Arte is around $40 and dominant like $60 and Kaplan around like $100. So they have different prices. Then the third study about the perception of samples had differences. We decided to do the samples had differences was because that we tried the first samples position first through a pilot study in Oberlin, and we found that players always say that the samples seems come back to the original position, but not exact the same position. So it's quite, it's extremely difficult to repeat the samples positions. So then we found that maybe samples had differences should be easier to investigate. So for this experiment, we make use of height adjustable carbon fiber samples from Anima nova. So one can increase the sample's height or decrease the sample's height by using a special tool just to turn it clockwise or anti-clockwise. So then the Anima nova samples has the minimum scale value is 0.022 millimeter for one graduation. And then we asked 19 subjects to participate, 13 violinists and 6 luthiers to do the playing test. So the first phase, we want to find the optimal samples head, and then the second phase to explore the perceptual threshold of head differences around the optimal heads, because luthiers all found that players were more sensitive around the good samples heads. So we decided to do this to explore the perceptual threshold of height differences around each subject's optimal height. For phase one, in the beginning, we set the samples head in a relatively lower height, and then we ask the players to play it, and then the experiment increased the sample size by 4 graduation, and ask the subject to play it again and to see whether it's become better or worse. If he say that this is become better, then the experiment will continue to increase the samples head. If he say that the samples, the violin become worse, then we will decrease the samples heights for a few graduation. So in this way, we can find an optimal sample set for the subjects. Usually it takes 5 to 9 trials to find it. And then we explore the threshold around each subject's optimal height. There are 10 trials, so 10 dart age. So 0 means that we don't change the samples at all, and 2 positive or negative value means that we increase the samples head or decrease the samples head. So first we ask them to play their optimal samples height first, again, and then we do dart edge, either not change or change it, and then give the player to play it, and they always compare with the previous one, and they say whether this is different, they are different settings or same settings. So when we change the samples height, and they say yes, you changed this difference, that is a hit. If we don't change it at all, that's the misrecognized, that is a false alarm. So we calculate the probabilities of hit and also the false alarm rates. Then we do the transformation for each rate and minus these two rates, and we can the D prime is what we want. So the perceptual threshold. And Claudia want me to explain here that so by this way, if one subject to say so all these to all these trials, he say that difference, yes, you change, then he get perfect hit rate, 100% hit, but he get a 0 for false alarm. So
yeah, so this is a method to take into account the bias so some people can have, you know, because
yeah,
we don't. I mean, it's not really good if somebody says, yeah, it's different all the time, because yes, of course, the hit rate is 100%, but the false alarm rate is very high. And the same for somebody who will say same all the time, the false alarm rate will be 0, which is perfect, but then it will miss the difference all the time. So so that's why you have to compensate the hit rate by the false alarm rate to actually see whether there was some really like some real detection. There was another thing that Lei you didn't mention. So the experimenter was Gary, and so he stayed in the same room, and so basically he would pretend to change the soundpost. He would make the same noise. So the makers and players who were taking the test, they couldn't know whether he actually changed something or not. Okay, so he took the same times, and if he was changing or not, just made everything the same. So they didn't know. But it was better for him to stay in the same room to actually shorten the duration of the experiment. I think at the end he was able to do it in less than a minute. Is that correct, Gary?
Yes.
Yeah.
Yes.
I mean, sometime it only takes 30 seconds or less, probably more normally.
Yeah. Okay.
Okay. Okay. In this way, we can abandon some bias. So whether you tended to say same or you always like to say difference, which will not affect the results. Okay, this is the result of the optimal sample set. So we collect in each subject's optimal sample set. We can see that it's okay. The y-axis is the optimal sample height relative to the original height. The original height is about 53 millimeter. So this is the relative height, and then it varies from the 0.1 to somewhere greater than 0.6. So this is actually relatively large range. So when we only change one parameter, the samples heights, and people don't agree with each other which one is optimal. And we see that the blue dots represents players' result, and the right diamond represents the maker's results. And we see the mean rating, the mean optimal height of the players is a bit higher than the makers, but maker has a wide confidence interval. This may be because that we only have 6 makers results. So, but this has to be interpreted by their perceptual sensitivity to the sample's heads. How big changes they can recognize, or how big change, or under how big changes they cannot recognize. So our phase 2, we calculate the perceptual sensitivity to sample's head. So the left plot is the probability that subject considered as different. So when the delta H samples head difference is 0, the P difference means it's false alarm rates. We can see that it is more than 70%. So it's very high. So more than 70. That when we don't change the sample's head at all, and people say, yes, difference, yes, changed. And it is even higher than the delta H equal 3 graduations. That is, this is the hit rate is less than 70%. And we see the right plot is the D prime, the perceptual sensitivity plot. And we can see that the confidence interval, the lower limits are all less than 0. So that means that people cannot recognize the height differences that we present. So when the samples height differences were 0.11 millimeter or less than it, people cannot recognize this sample's height. So then we also do the bridge admittance measurement for different samples heads. And we can see that see the legend from the legend represents the graduations we increase. So from 0 to 30 graduations. And this was denoted by from blue to magenta. And then we can see that the A0 mode, the frequencies generally stayed about the same from blue to magenta. So when we increase the samples heads, the frequency of A0 mode generally don't change. We can see the B1 minus mode from blue to magenta, it has an increased tendency. That is to say, when we increase the samples heads, the frequency of B1 minus increased as well. And this is different. This is opposite for B1 plus mode. We can see that from blue to magenta, it has a tendency to the frequency has a tendency to the left. So when the samples head was increased, the frequency of B1 plus was decreased, and we see the magnitude almost for all three modes. The blue line was higher than the magenta lines. So when we increase the samples height, the magnitude were all decreased. So this is easier to understand, I think, because when we increase the samples height and the plates around the bridge become more rigid, so it cannot we use hammer to tap it, and it cannot vibrate easier. And because the playing test in the samples had differences, because in the playing test, the players cannot always compare two setup at the same time. They might forgot what the previous one sounds like. So we did a listening test instead, and in this test we can test bigger samples height to see whether they can recognize it. So we make a recording by our soloist, Nathan Shem, and he will also come for this conference as well. So, then we when there are 21 subjects come to this test, 13 violinists and 8 luthiers, and this and they do a pairwise comparison. So eight pairs and 8 pairs in each test, and in total 16 pairs. And the comparison, the perceptual sensitivity was calculated similarly as in the playing test. So we have delta H equals 0, and actual height. So 2, 3, 4, 6, 9, or 12 graduations between two samples heads. But what is different is that for the zero delta H, we employ two reference pairs. We use identical recordings for reference pairs, and also different recordings of the same samples had for reference pairs, because we want to because the player, we ask the player to always play same as possible, but he cannot do that. So we want to make this influence as small as possible, and so we employ this reference pairs. And this is our computer interface. We ask subjects to push the button to listen to a pair of songs, but please ignore variations in playing technique. And each pair will be played in A-B. And you can choose whether this is the same setup or a different setup. If you feel this is a different setup, please describe the differences between them. Because this is a PDF version in my iPad. I want Claudia to play it.
You said that it was maybe possible, but it doesn't work.
Yes, it doesn't work. I cannot share screen.
Yes, I will do it, okay? I've prepared it, so it's ready. So I need to, can you stop sharing your screen? Because I need to share so for the audio. Can you hear something?
Yeah.
I cannot hear, so it's weird for me. You have to tell me if it's finished because I can't hear it.
We can hear you play it. So the first pair is two recordings of one same soundpost height. And the second pair will be two recordings has the delta H of 9 graduations.
Okay, so Lei, can you show me with your thumb when it's over so I can move to the next one, okay? Because I don't hear it, I don't know why.
Okay.
So I play again the 2 recordings of the same soundpost height.
Okay.
Now 9 graduations difference.
Okay.
Okay, so I will stop sharing my screen and you can. Okay, sometimes something is. Okay. So yes, just so to complement. So basically with the listening test, we thought, okay, we can overcome this problem of having the changing being done successively, because now you can almost listen, very fast between 2 different soundpost heights almost at the same time, which you can do when you have to change it in live. Okay, so we thought it would be easier for people because they can really compare a few times the 2 soundpost heights. But then the problem we have now is the reliability of the player. And so even if the player is used to play as reliable as possible, is a top player, yes, it's not that easy. And so it's hard for the listeners to know whether the change is due to a soundpost difference or to a playing difference.
Okay, here is our result. Is our result, and the left corner is the hit rate. That's we have samples had difference, and people recognize them correctly as difference. We can see that one samples had differences is 3. It's significantly higher than 2 and 4. And then from 6 to 9 to 12, it seems increased. The hit rate increased as the samples had difference increased. And we see the false alarm rates, and the reference pairs S1A, and the right dot is that we use identical recordings, like we play A or B, and they misrecognize them as different, and the probability is very low and lower than 20%. And the reference pairs as 1B, that we use different recordings is of one same sample set, and this become higher, is about 50%. But when we record in the playing test, it's about 70%. So in the listening test, the false alarm rate is remarkably lower. Okay, we answer this question later. And then we calculate the perceptual sensitivity to samples had based on these two reference pairs separately. The right line were calculated based on reference pairs of S1A, so the identical recordings. We can see that all D prime were higher than 0. That means that subjects can recognize all the different stimuli we presented. But we see the blue lines. This was calculated based on reference pairs as 1B. So different recordings of same sample sets. And in this time only when the samples had difference is 9 graduation or 12 graduation, the D prime is higher than 0. So this means that people can recognize 9 graduation and 12 graduation high differences only.
Yeah, Lei, before you go to the next slide, I just want to make sure that people understand the difference between the two lines. So the white lines, basically what it means is that everybody was able to detect differences between the two stimuli, okay? When there was a difference in the sound post height. The problem is we don't know whether they said it was different because the playing was different, or because the sound post height was different, or because there was a change in the timbre of the violin due to the sound post height difference, okay? And so if you look at the blue line, now the blue line is much lower. It's only for the highest graduation that it's above 0. And that means that in the case of the blue line, we are pretty confident that for the highest graduation, what they hear is a real change in terms of sound post height, and not just a change because of playing differences.
We see for the right line, there's a value for sample height difference equals 0. This is, we calculate the reference pairs as 1B based on the reference pairs as 1A. So we can see this D prime is also higher than 0. This almost explains that subjects could not differentiate the differences caused by playing technique from the differences caused by sound post height. So this is the disadvantage, the main disadvantage of the listening test. And then our conclusions for the sound post height perception experiment. Subjects' optimal sample height varied from 0.132 millimeter to 0.616 millimeter relative to the original sample height. This range is well inside the extreme sample height we ask subjects to test it. And this range need to be explained by the threshold, perceptual threshold. However, in the playing test, we didn't have a good result because subjects could not recognize the soundpost had changes we present. So they cannot recognize 0.11 millimeter or less at better than chance levels. Actually, we did this, we designed this experiment was based on a pilot study, and the pilot study is similar as the recording of the listening test. We was expected people can recognize 5 graduations or less, but at the end they could not. And in the listening test, we found that subjects could differentiate soundpost heads with a difference of 9 graduation and 12 graduation at above chance levels. So this is also very tiny, maybe confirms the luthiers saying that any changes they made on the soundpost head will make a significant difference on the sound on the violin. But Claudia just mentioned another point a few days ago, is that in real life, luthiers didn't do didn't change the soundpost heads only. What they do is always they take out the soundpost and they make some change. They may make it shorter or anything, and then they put it back into the violin. So in this process, they should not only change the soundpost heads, but they maybe also change the position. And then the final conclusion is that we found the false alarm rates were much lower in listening tests than in the playing test. And future work, for the first study, we want to recruit more subjects with various degrees, because we only have 9 subjects, it seems, to fill, and especially more professional musicians, because we already found they seem have more agreement between these groups of musicians. And then we want to try maybe performance live violins for string experiment to expect for more significant differences. And we want to and could employ strings of quite different qualities. Maybe we can expect more significant results. And also we can investigate the perceptual sensitivity of subjects to greater soundpost height differences. Maybe we can have can reach the true perceptual threshold in the playing test.
Yeah, maybe about this is like, maybe we were a bit misled by you makers who all say, oh, you can just shade the soundpost, it makes such a huge difference. So we really thought that we would see a smaller threshold than what we have.
Tú vas a estar mirando los demás cuando está hablando otro. Sí, me he olvidado un poco, pero...
Somebody else unmuted, isn't it? Yeah, so we were a bit surprised, and that shows the difficulty of, testing some beliefs that makers can have, and which doesn't mean that our experiment shows that your beliefs are wrong. It just shows that the difficulty of actually testing this rigorously, because it's easy to see effects with 1, 2, or 3 players, but when you want to actually do it systematic, and then you realize that, hey, actually the false alarm rate is very high. So the differences are, people are maybe not that sensitive, or at least less than what we think they could be. Or maybe it's because the test could be designed a bit better, but then we haven't found a better way for now. But just to show that something that could, yeah, oh yes, everybody agrees about this. And then when you really want to test it, then actually it's not that obvious.
And the false alarm rate is very high. So this is maybe the tendency that players tended to act when luthiers do some adjustment to the violin.
I can make a couple observations also, maybe.
Okay.
I would just say, especially for the playing test, some players had a much more defined and rigorous process of evaluation than others, but that didn't necessarily make a difference in their accuracy. And there was one subject who actually had no false alarms. And he was a professional player who said that he grew up playing games with his father, passing violins back and forth and making small changes. And so he was very heightened sense of maybe changes on the instrument. But in general, it was kind of surprising how inclined people, the subjects were to believe that we were really making changes when we weren't necessarily always making changes, even though we told them from the start, I may make a change, I may not make a change. All you have to say is whether you think a change was made or not. But they really seem to be inclined to believe that a change had happened.
Okay. And we thank Kermit and CSC for the funding these studies, and also thank Nathan Jim for the listening test recording, and these violinists for interviews or helping, and thank the luthiers, and they helped adjust the soundpost or give suggestions for the experiment. And thank senior and junior Paul Mona, and they invented and loaned the Anima Nova samples to us. And thanks Fanta for provide the strings or for the string experiment, and also thanks all the violinists and luthiers they participated in the experiments. Okay, thank you.
Thank you, Lei.
Thank you.
Okay, any questions? Raise your hands in the participant panel so I can. Oh, there was a question from Ruth, so maybe you could start with it. So she was wondering about the amplitude of the signature mode being smaller when the sound, I suppose she wanted to say the sound post was higher. Could you go back to that slide maybe?
Yeah. Oh, this slide. So yes, when the soundpost going higher, the magnitude was decreasing. What he was asked.
The amplitude of the signature modes are indeed less when the soundpost is height is increased. Because you start from the blue, which is 0 graduation, to 30 graduations. And you can see that the amplitude is going down. So A0, B1 minus, and B1 plus. So yes, indeed, it's going down. Any other question?
Did you try making it shorter?
Try making soundpost shorter?
Yes.
It's impossible.
We started with a very short, and if shorter than it will fall down. We started from a very short soundpost height.
This is the way you should work with Anima Nova. You insert it being very small, just at the limit of fitting, and then you increase. That ensures as well the bearing to really fit properly, and when you increase the height. So you can't make it shorter because it will just fall.
Okay.
I could just add quickly. I mean, I'm not a string player, but it was very easy to change the height after I got used to it. So my kids play cello, and it seemed like a nice option for making changes, especially in Montreal, where the weather conditions change so drastically from summer to winter. It's quite easy to, once you have it in there, to make adjustments and to experiment with that. I don't have any stock in the company, but it seemed like a nice option.
Romain's question is about removing the accelerometer between each measurement. I think this time you just measure them in a row. You left everything and then you were increasing the length, didn't you?
Yes, we just gradually, we cranked it up a little bit, made a measurement, increased the height a little bit, made another measurement. Yeah. So we may have also done it on the way down. I don't remember. Lei might have some notes.
I need question.
Yeah, with regard to the setup of the student violins, I'm specifically wondering about things such as string height or the smoothness of the neck that might affect player preference, but not the sound as much. So he's talking about your first experiment.
So where is the question?
It's the last question by...
okay, what was done with regard to the set of the student violins? I'm especially wondering about things such as string height.
Yeah, he's wondering whether they were set up properly.
Yeah. It's quite a while ago, so I don't remember perfectly, but there were some issues, and we tried to get the instruments at least in good working order. I think one of them had to be repaired or swapped out for something else, but we didn't necessarily make sure that they all had the same exact setup in terms of string heights and things like that. So that could be a factor.
Yes, actually because we asked them to wear dark sunglasses and reduce the light, they cannot see the appearance, but they did mention that this violin has a flight neck, or this string height is very, very high, or this one is very low. They mentioned these things. But in our experiment, this will not affect our results, because we do not use same making violins. We use different violins, but they will not affect our results.
I mean, it will affect the player preference, but
yeah, they affect player preference. But not the sound as much. I'm not sure.
What is interesting in the study is, like, if you actually take randomly one of the student violin actually didn't perform bad at all. And so if you compare this violin with the performance violins, you wouldn't see anything. So if you look at individual violins, just take the 6 violins, you don't really see any statistical difference between the violins. But if you actually group them by 2 groups of 3 violins, then you see a statistical difference between the 2 groups. Okay, and so so that means that if you just look at individual violins, you may not see things just because of the big variability. And I basically had the same in my Strad versus new study. If I look at individual violins, the difference is not necessarily significant. You know, the first violin was new, but the second violin, which was very close, was old. And if you compare these two violins, there was no statistical difference. But then if I group all new violins and I group all old violins, then I could see a statistical difference between the two groups. And this is because of the big variability between players, of big disagreement. And so it's not easy to really get like fine differences just because people don't agree, which is as well probably the greatness about this is like you will all make an instrument that will find a buyer. Any other question? It's hard to follow the chat at the same time as answering and. Any other question?
Claudia, can I ask a question?
Yeah, sure.
Because I did some similar tests this year actually with some other brand adjustable soundpost, but yeah. I'm not focused on the bridge admittance because I find it's very hard to find any difference on the bridge admittance. Instead, I'm doing some tests on the vibration mode of the whole plate, the top plate and the back plate. I think it's a little bit easier to find the difference after you change the height or the tightness of the soundpost, or after you change the position of the soundpost.
What are you measuring? Sorry, I didn't get it. The connection was not so good at that time.
So I think after we use this kind of adjustable soundpost, we do notice some differences during the playing, or we can notice the differences while we are listening to it, right? But yeah. But when you're looking at this bridge admittance, the difference is very small, right?
Yes, but at the same time, I think they correspond to what we have seen is that people, when you try to test them, people cannot tell relatively the difference.
So instead of bridge admittance, I'm trying to do the vibration mode animation of the whole plate right now. So it might be easy to look at the difference after you changing the height of the soundpost.
Okay.
Maybe, but at the same time.
Yeah, I'm still working on it. I don't know what we will get in the future, but I just want to mention this point.
Yeah, but at the same time, the physics goes with the perception. We haven't, I mean, our perception study shows that people were not able to reliably test the differences. And that kind of makes sense because the differences are still very small.
Okay.
So to some extent, it makes sense.
Yeah.
But I'm not denying that, some other measurements may highlight better the differences, because here, for example, it's 30 graduations different, and it's quite a lot. And we didn't test this as much as this in the perceptual test. So indeed, the differences could be better highlighted with some other measurements, maybe.
Okay, thank you.
I wanted to ask a question, please. So we see on the spectrum that when soundpost is higher, the amplitudes of the lower body modes go lower. But what about the higher frequencies, the higher modes? Do you have any data on that? What is happening to it?
You mean as the soundpost height increase or decrease, how the higher frequency magnitude changes?
Yes, exactly.
We did have the plots, but we don't find some clear tendencies, so we don't show in here.
Gotcha. Okay, thank you.
To answer some of the question about anima nova versus wood, so we did some pilot testing where we actually compared the violin with the anima nova and the violin with a wooden spruce. But this was not only in the pilot study. We didn't actually use it in the end. Just because the problem as well with the spruce, I mean, of course, it can make a difference because yes, it's not the same weight and everything, but at the same time, it's difficult to put it at the same position as well anyway. So we didn't investigate this further just because we didn't have time. And we still haven't found any good way to measure reliably the position of the soundpost. So if we want to actually compare different soundposts, we have to find a way to put them at the same position. Plus, the anima nova is made so basically the bearings will always fit. And then if you make a spruce, you are never completely sure if you move it slightly around. I mean, your job is to actually make it fit. But so some of the differences could be because the fit is not as perfect as with the anima nova, or because of the weight of it, or the carbon fiber versus wood. So there are plenty of effects which would need to be investigated, but yeah, was not possible in the course of Lei's PhD. We stick to the simple, which was the height, because this we think we could reliably measure, and even this was proved to be harder than we had expected. So